Okay, so let's review a little bit about what we've talked about so far. Because we had a really kind of lively discussion last class, and it can kind of feel like we haven't learned anything concrete yet, but I think we have, and I want to remind you of what we've done. So for one thing, we've said, if you have a structure that is being loaded in some way, what you're doing is you're storing energy in that structure. And because the type of deformation you're doing is going to cause strain, this is typically referred to as a strain energy. And we can write down what the strain energy of a structure is. And it's typically denoted U. It's a type of potential energy. It's the amount of energy you're storing in this object. There's no kinetic energy. Nothing's moving. No inertia. This strain energy is equal to half the integral over the volume of the stress times the strain in that elastic body. And then what we did is we started to use some relations that we have from mechanics of materials and really just applying Hooke's law. And we were able to kind of split this energy up into different contributions. So there might be a contribution there's going to be a contribution that is going to primarily act to stretch or compress this object. So the amount of energy you're storing in the stretching energy of your object is, let me just write down that I put these things together, is you can either write it one of two ways. You can write it as 1/2 the load squared over EA integrated over, oops, that's not right, integrated over length. This is for a 1D bar. You could write down and derive your stretching energy for a 2D surface, or you can write down just in general for a 3D surface. But conceptually, to get a feel for how this works, if we just think about 1D, we can actually learn quite a bit. So we know that our stretching energy can be either written in terms of the applied load, or it can be written in terms of 1/2 the, let's see, let's write this a different way. EA over 2 times the integral along the length of your strain squared dx. I pulled out the EA there, which is what you can do if the modulus and the cross-sectional area is uniform along the length x. If it's not, then you keep it in the integral, and it'll have some functional dependence on x. And so when you integrate over x, it'll be part of the variable that has some dependence on x, and so you'll have to account for that in your integral. So pulling it out is what you can do if it's constant cross-sectional area, constant material properties. So this is your stretching energy of a 1D bar, your bending energy. Again, you can write it down in terms of the applied load, or you can write it down in terms of instead of a strain, we would write it as a curvature. So if in terms of the applied load, this is a B. You have the integral of the length of the moment squared over EI dx. Or again, if this EI is constant and we know a curvature, then we can integrate over the length for curvature squared dx. We talked about how the strain energy in torsion is of basically the exact same form as your bending energy. It's just that instead of thinking of a moment, you think of a torque. Instead of thinking of your second moment of area in Cartesian coordinates, which is I, you think of your second moment of area in polar coordinates, which is J. And so you get the energy you store in torsion, we'll call it UT. And that's going to be equal to 0 to L, your torque squared over GJ dx, or GJ over 2 integral of your amount of twist squared. So I'll highlight that just to remind you. Amount of twist. This is your amount of curvature. And I think epsilon is pretty familiar as the amount of strain. There's one more I didn't give you. I'll give it to you now. It is probably it tends to contribute less to the energy stored in an elastic body, except in extreme circumstances. Extreme circumstances means thinking about 1D objects. It would be a really short beam or really well, I don't know what the opposite of slender is. Slender would be if its other dimensions are really, one dimension is really thin compared to its other lengths. If it's not really thin, if it's a really kind of stout, short beam, then you're going to store some energy in transverse shearing. Transverse shearing, for those of you who don't remember from mechanics of materials, is kind of like what, take your notebook, if you have a notebook in front of you, and if you like bend a stack of pages, you can look at the edge of that stack of pages, and you'll see that they kind of slide past each other, right? They kind of like the top one will slide. If I bend this thing a lot, the top one has slid up relative to the bottom one. If you imagined doing that little experiment again, but instead imagine that you glued every sheet of paper together. Now if you bend it, kind of can fix that end, it wants to shear those pages past each other, but there's a glue or some sort of adhesive that's resisting that ability for it to slide past each other. That stress that you store in kind of resisting that shearing between those two pages is your transverse shear stress. What is G and E here? Yeah, good questions. G is your shear modulus, which it measures the, or modulus of rigidity, which is the measure of how hard or easy it is to distort the shape of an object. So, do I have an object in here? Yeah. So here's a cross-sectional, here's an object that's a parallelepiped. It's basically a rectangle in 3D. So the shear modulus of this object is a measure of how hard is it to distort this from something that's kind of got a rectangular shape in all directions to something that might have like a true parallelepiped where you have a kind of a, if you think of like a parallelogram in 3D, you've kind of fundamentally changed the shape from rectangular cross-section to parallelogram cross-section. That's what G is measuring. E is measuring your modulus of elasticity, which is really measuring how hard is it to keep the same shape but change the lengths. So this is a rectangle. I stretch it. It's still a rectangle. It's just longer in these directions and smaller in the other directions. So E is measuring that. Young's modulus. G is measuring distortion of shape, modulus of rigidity, shear modulus. T is torque. M is your bending moment. They're both couples. I and J we know. 0 to L is the length of our 1D beam. We're integrating over X. X is the coordinate that runs along the long axis of the beam. So going back to the transverse shear, what am I going to call this? We'll call this UV. Transverse shear is a little bit of a pain, as you probably remember. We'll call it UV. And your transverse shear, you can kind of guess, right? If your strain energy and stretching depends on your axial load squared over your cross-sectional area times your modulus, your transverse shear is going to depend on your shear load squared over your shear modulus times your cross-sectional area. So it's going to look a lot similar to the stretching energy, except there's one more thing that you have to keep track of. It is that there's a geometric prefactor that enters alpha, GA. Okay, what is alpha? Alpha looks kind of awful, but two things. It's just a number, and it's a number that is measuring a geometric property of the cross-sectional area. So alpha is the cross-sectional area over your second moment of area squared. Now here's where it gets awful. Times the integral of your first moment of area squared. Does anyone remember the first moment of area? I'll show it to you in a second. Over your width squared, integrated over the cross-sectional area. We could work on figuring out how to calculate these things. I don't think it's particularly important. If you run a beam analysis in COMSOL, it's going to spit out half of these things for you just by drawing the thing in CAD anyway. But let me tell you what it is, just so you know what you're actually using here. Q is your first moment of area. First moment of area. Now this can depend on which direction you're choosing to measure this relative to, but for right now we're just gonna keep it kind of simple. Q being your first moment of area is the integral of where your area is relative to the neutral axis, so y. So if you have something that is a rectangle, the neutral axis runs right through the center of this rectangle. You could go with your y-axis would be 0 at the center, and so it's asking you to integrate along y over the area. This is your first moment of area. It's your first moment of area because y is to the first power. Your second moment of area looks exactly the same, except, you're integrating y squared dA. I suppose we could define a third moment of area, which would be y cubed. I don't think it has any physical meaning. But these two properties, probably more than anything else, and the combination of this thing, Q, and transverse shear is probably the things that causes engineers in mechanics of materials and structural mechanics the most frustration. I will say, I think it's not that important. I mean, you should know about it. You should be able to calculate it. You can calculate it. I think oftentimes it ends up being like a slight correction to what you would get if you were to simply ignore it. So we'll go through that in a second. I'll give you a sense of what your transverse shear is doing to affect your predicting your deflection or something like that. So maybe maybe that's blasphemy, maybe I shouldn't say that, but I think it's kind of, it causes a lot of headaches, but I don't think you're gaining a lot for those headaches. So, but that's what it is. So, and I just would bring you back here for a second. This looks almost exactly like the, oh yeah, thank you for the question from Kanani. It should be integrated over dx. The point I would highlight is this looks exactly like your stretching energy. Let's see here. Where it is a force squared over GA. And you can see, you can kind of start to recognize stuff. And this is where I think it's actually really powerful conceptually. Just look at how these things pair. Axial load, P, pairs with your elastic modulus, because your axial load acts to stretch an object. Shear load pairs with your shear modulus. Your bending moment pairs with EI, your elastic modulus, times your second moment of area. Your torques, which cause twisting, which tend to distort areas. So like if I twist this thing, I'm tending to distort the cross section of this shape. Even if I was to kind of slice through there, you would see there's kind of curves undulating along this whole object. So your torque is tending to distort the shape of your object. Whereas look, if I bend it, if I cut here, it's still primarily a rectangular cross section as I cut this object. So bending it is acting really just to stretch the top of this thing and compress the bottom. So it pairs with your elastic modulus. Applying a torque tends to distort your shape of your cross section. So it pairs with your shear modulus, which measures how much energy it takes to distort the shape. I point these out because I think these types of relationships are important for you to kind of see immediately. The forces or moments you're applying should pair with the things that tend to resist those deformations. All right. So from here, we did a couple things. One we did in class explicitly, and the other one I asked you to read, but I'm going to briefly remind you of them. From here, we said, well, hey, actually, this is all for a 1D bar. From here, we said, hey, I can compare my bending energy to my stretching energy. And if I do that for my 1D bar, and I ignore my factors of 2, what I'll find is that I get a relationship that says the bending energy to stretching energy goes as the thickness squared times some ratio of how much you've bent it versus how much you've stretched it. And the key thing here is this thickness squared term. And what we learned is that thin objects are easy to bend and hard to stretch. And this confirms stuff that we're familiar with, and it also starts to explain, at least qualitatively and conceptually, why elastic instabilities like buckling happen, because you're trying to compress something that doesn't want to compress, it really wants to bend, so it buckles and it bends. The other thing we learned is that thin objects are easy to bend, hard to stretch. In 2D, So for instead of a beam, we think of a plate, or 2D with curvature, so a shell. What we learned is that you can measure, let's do this up here. What we learned is that you can measure the curvature in the two principal directions of your object. Call it kappa 1 and kappa 2. And we learned that there's three options. Either one of these curvatures could be 0, both of them could be of the same sign. Doesn't matter if it's positive or negative. Or they could be of different signs. Oh, that was terrible. And the product of these two curvatures is what's known as the Gaussian curvature. And there's really only three options. Gaussian curvature is either 0, it's positive, or it's negative. And to switch, we learned that there's three options. Your Gaussian curvature could be 0, positive, or negative. And to switch between these two types of things, so to change from a flat sheet to a sphere, you have to stretch. To change from a saddle to a sphere, you have to stretch. To change from any of the combination of those shapes, you have to stretch. Now, combining these two things together tells you quite a bit. If you have to stretch to change from a flat sheet to a sphere, and thin things don't like to stretch, then you're not going to be able to wrap a sheet of wrapping paper around a basketball. It'll be fundamentally impossible. It'll also allow you to design structures by changing something very, very subtle, which is I can take my sheet, hang it over the edge, oops, and it'll bend a ton. But if I just simply take my sheet and add a tiny amount of curvature to it, just like I'm lifting up the edges by a millimeter, and now it doesn't bend at all. Because to do so would require it to change its Gaussian curvature, which it's not going to do because that would require it to stretch, which is really too hard to do. So this is a subtle difference in this structure. I just literally tilted the edges by a millimeter. and look at the deformation response. This thing is a huge overhanging cantilever. I let go, and it sags by almost the entire length of the sheet. That's a huge change in structural behavior by changing a very small thing. But the key is that it's all driven by your intuition. If you know that you have something, add a little bit of curvature in one direction, it makes it stiff, because bending it in a different direction would require it to change its Gaussian curvature, which we know it can't do because it's really expensive to stretch a thin object. That's what your little h squared term there is telling you. All right, what else have we learned? We've also learned that building on this idea that you can kind of compare these energies, unlike what you do in statics, mechanics of materials, physics, we know that there are kind of fundamental laws that tell us that the forces must balance. There must be a force balance. There must be a moment balance. These come from really like fundamental laws and behaviors that have been observed for millennia. There's no law that says energy needs to balance. However, what you can do is if you can write down the energy of some deformation, so for instance, the energy to bend an object, and you can write down the energy that some force contributes to your object, so say gravity that's acting on it, what you can typically do is ask the question, at what length scale, or in some problems, at what time scale, are these energies roughly the same? And what that tells you is if your length is larger than the length scale, that these things are balanced, you're going to see one type of behavior. And if it's smaller, you're going to see a different type of behavior. What do I mean? Let's go back to our sheet. So let's come over here and say, and we could say, well, let's just find out what length scale gravity and bending balance each other. We know the length scale for bending. Okay, so let's do this really quickly. We know that our bending energy is equal to EI over 2 times kappa squared dx. We can approximate and say, well, let's not worry. We only want to know when gravity is going to just start to bend our object to a small amount. So we can make a small angle approximation in here and say curvature, we know, has some complicated definition related to, well, I'll just show you what it is. You might not remember. Curvature does this. It's like the second derivative of deflection over 1 plus your first derivative of your deflection, which is your slope, squared. Oh, I might not have enough room. Let's see if I can do this. And all of that stuff in the denominator is raised to the 3/2. That's the definition of curvature. It's just a measure of how quickly is your slope changing and how quickly, so that's kind of what this top term is saying, is like what's the change of your slope as you move along it. Change of slope is roughly curvature, and this is just actually your slope. So you say if I have small slopes, this term on the bottom here goes away. Right, we'll say the first derivative is really small. And if we say that's really small and it's squared, then it becomes really, really small. And then you basically have 1 plus an incredibly small number raised to a power, who cares? 1 to raise to any power is going to be 1. And so we could say this is approximately equal to that. Okay. So we'll say this is approximately that. Second derivative squared. dx. We can make a further approximation and say, let's just pretend that our beam will bend into an exact circle. Is it going to bend into an exact circle? Probably not. You know, this is not really an exact circle, but near the point where my fingers are, it's pretty circular. If we can say that if it'll bend into an exact circle, then we know that our second derivative, then we know that the radius of the circle, which is equal to 1 over kappa, will basically be the length squared over your deflection. It's kind of like saying this. I've got my circle. I'm going to say, here's my cantilever up here in red. My circle has some radius. This thing here, my deflection here is going to be my W. And we'll say that the length of my red object is L. The radius of this circle is approximately equal to your length squared over W. If you're interested or this doesn't make sense, we can chat about it in office hours or something. It's a simple approximation. And so then this thing becomes roughly EI times that whole thing squared, so it's W. So flip this thing upside down and square it, so you get W squared over L to the 4th. And then we're going to integrate along the length, so we get an extra L. So we get EI W squared length cubed. So the bending energy, the energy it takes to bend a beam into a circle, a part of a circle, is basically the bending rigidity, EI, times how much you bent it, squared, times the length of your beam cubed, over the length of your beam cubed. We want to compare this energy it takes to bend into a bit of a circle to the energy that gravity is acting on this object. And our gravitational potential energy, again, I can write this down, but it's going to be, I'm just going to tell you how it scales. If we can chat about where it comes from if you want later. It's going to scale as the thickness times the width times rho g times the deflection times L. This usually confuses people because they're used to thinking that the gravitational potential energy is like mass times gravity times height, right? mgh or something like that. It's a little bit different here because you have to ask yourself, well, what's the reference frame that I'm comparing to? And what the reference frame is the end of the beam. So like here's the point I'm trying to make. What you're trying to say is how much is gravity bending one portion of the beam relative to the portion that isn't moved. So typically we think about gravitational potential energy as like, if I lift up my object higher, I have more gravitational energy, potential energy stored in that object, which is still true here. Like obviously if I drop this from here versus if I drop this from here, there's more potential energy in this whole structure up here than down here. But that's not what we're talking about. We're talking about how much is gravity bending this object. So look, if I'm here, the deflection of my beam doesn't change if I double my height of my arms. Gravity is acting on this beam uniformly, and we're trying to say how much is gravity bending one portion of the beam relative to the other portion of the beam. So you can kind of think of it as there's kind of two types of gravitational energies. One is going to be one that's causing it to bend, and the other is going to be how much is energy stored in there if I were to drop the film. We're not talking about the latter one. We're talking about the former one, and that's where this equation comes from. And so the question, going back to the question we're asking, we're saying, at what length are these energies comparable? So you can just literally equate the two of them and solve for the length L at which gravity and bending are of the same order. And if you do that, if you take H, let's do this a different way. If you ask yourself, when are these things approximately equal? Then what you can solve for is what's known as the elastogravity length, which scales as EI. Well, technically, no, hold on. Sorry. I'll make this subtle difference in a second clear. It scales as the bending rigidity over rho GH. I haven't told you what bending rigidity is yet, but I'll tell you in a second. So if EI is EH cubed B, then their bending energy is, the bending rigidity is EH cubed. It's kind of like EI per unit width. So the widths all got canceled out here because there's a width appearing here in your gravitational energy, and there's a width appearing here in your I. So those B's cancel out, so they disappear, so we use a slightly different notation here. Okay, what does this mean? We are asking, at what length is the energy acting to bend an object comparable to the energy required to bend an object? What that means is, if you plug in numbers for that, there's a length below which gravity doesn't really deflect this object much at all. So you looked at it, it's basically flat. Now, to be completely honest, anytime you put your sheet over the edge of your table here, gravity is deflecting it a little bit. What we're talking about is, when is gravity deflecting it a lot compared to the length that's hanging over? So you can start to see as I get a little bit longer, my sheet's a little bit bent, so it's got a little bit of extra stiffness to it. But now you can see, clearly now it's deflecting a lot. So the question is, what this length tells you is, when do I have to worry that gravity is going to start to deflect my object? So say you were trying to make does anyone know what an atomic force microscope is? Atomic force microscope is a cantilever that you shine a laser at, and you use that and you basically vibrate that cantilever and then drag it over surfaces. And then depending on how the cantilever deflects, you kind of know how it's supposed to deflect because you basically just do this to it, and you know what it's supposed to do. But if it touches something, it kind of gets a little bit, it'll either deflect more or less. Based on how much it deflects, so you shine a laser on it, it'll kind of tell you how much it's deflecting. Relative to how much you expect it to deflect, you can measure what's on the surface of anything you want, and it'll tell you exactly what that surface looks like based on how this thing bounces off of it. So you might want to make a new fancy atomic force microscope with a new cantilever, and you want it to be incredibly light and have these special properties made of some special material. You might ask yourself, well, is my cantilever going to be perfectly rigid? Or is the new material I'm using going to cause it to bend a little bit under its own weight? You don't want that latter one, because if you don't have that in your model, then you're going to calculate the wrong deflection as it shakes, and you're going to calculate the wrong surface topography of the thing you're trying to measure. So this can kind of tell you, oh, okay, is my object deforming under its own weight or not? So here, when I have it just slightly hanging over the edge, you can say, yeah, the object's really not deforming much under its own weight. If I change my length a little bit, the object clearly is deforming a lot under its own weight. The length at which you start to see the object deform a lot under its own weight is this length. And we found this just by asking, when are these two energies comparable? You could do the same thing with asking when will a fluid bend an object? I'll do this one even quicker. Elastocapillarity. Bending energy is exactly the same, but you could ask yourself, well, when will surface energy, so we'll call that our surface energy. This is the tendency for a fluid to want to either wet a surface or ball up on a surface. And it's a really simple formula. It's a material property that depends on the two surfaces. The material that the fluid that you're wetting and the surface that is wetting on. So it's this quantity integrated over the area, dA. So you get a cross-sectional area here times gamma. Up here you have a cross-sectional area H times B. Or there's H cubed, but you'll have two H's left. And so the end result is, and this is what we saw in the paper that I had you all read, is that there's an elastocapillary length. That's your bending rigidity over your surface tension, and there's a power of 1/2 to it. What this length is telling you is when will a fluid cause fibers to bend. So you can imagine saying, the simplest thing that I gave you was in the paper, where I said, imagine a cylinder of radius r, and imagine putting a flat sheet on top of it. And now just imagine that cylinder is wet with a fluid. The question that this is answering is, when will that surface tension be able to bend that sheet around that cylinder? You can imagine if that cylinder is incredibly small, it's not going to be able to, it's going to take a lot of energy to wrap this sheet all around there. And you can imagine that if the surface is flat, it takes no energy to bend it on there. I mean, it's covering the surface without that. But this is also used for a lot of people are making like microfluidic devices in soft robotics, in lab on a chip diagnostics, where you want to move small amounts of fluid in places. Well, to do that, you have to make really small channels. And you have to put fluid in there. And if that channel is small, it's usually thin as well. Usually you have a kind of a thin membrane over this thing. There's a length to that channel in which, if you're below that length, the fluid will pull the kind of top of the channel down, and it'll just plug the channel. It'll just it'll bend the kind of, here's your channel, between two sheets of paper, but just imagine this thing really small. There's a length, that length, that'll tell you whether or not your fluid is just going to cause this sheet to be bent down, which is not going to let any fluid flow through your channel. If you're using fibers to kind of pull up a fluid with a capillary action, this length will tell you if those fibers are too soft, the fluid is actually going to cause them to coalesce, and it's actually incredibly hard to get those fibers to separate again. So these things give you an estimate of, by just comparing kind of two energies, they give you an idea of at what length scale will those things be comparable. Above that length scale, like the gravity length, gravity wins, your sheet bends. Below that length scale, bending rigidity wins, your sheet stays flat. So there's a lot we can do conceptually just by looking at these energetic scalings. The next thing we're going to do is get a little bit more quantitative about stuff. And so before I do that, what questions do you have on any of this stuff? This is really probably all just review from what we've done so far. Are we all okay? Give people 1 second to jump in. All right, let's look for a second and just sanity check. Strain energy is 1/2 stress times strain over the volume. If we look at this with just looking at our units, we know this is an energy because I'm telling you it's an energy, but let's double check. I use this notation here. I think it comes from chemistry, but I don't know, I use this notation of square brackets to say that I want to evaluate the units or dimensions of an object. So I want to know what the dimensions of this thing are. So we can ignore our numbers. We have the integral of the dimensions of stress, dimensions of strain, dV. So stress is easy, newtons per length squared. Strain is easy, it's dimensionless. So we can just say it's length per length. And now the integral of a volume, we don't know how to do the integral explicitly because I haven't told you how sigma or epsilon depend on x, y, and z. But we do know that regardless of how they depend on x, y, and z, this integral is going to give us a volume. It's going to give us a length cubed. So we're going to get another length cubed here. This makes sense. Length cubed, this cancels out with this. These are dimensionless. And as you would expect, we have, I guess I shouldn't have used newtons in length. I should have used force. Well, whatever. So we'll convert this back to newtons per meter. And I'll just note that I switched this length to meters. The actual, when you do dimensional analysis, your choice of the unit system doesn't matter. Like, it doesn't matter if we choose meters or inches or pound foot or whatever. The key thing is the fundamental dimensions of length for force, which isn't even a fundamental dimension. Force is mass times acceleration, so it's mass times length over time squared. Doesn't matter. The end result is you get that the units of energy are newtons per meter, joules. But we're going to keep it here for a second. Why? Well, if I take the derivative of my strain energy with respect to a force, what are the units that are going to result from that? With respect to a force, we'll call the force, how am I doing it in my notes so I don't mess it up? P. No. Okay. Do. we'll do N. So axial force. If I take my derivative of my strain energy with respect to a force, what are the units that are going to result from that? It's a lot simpler than it looks. Just the length. Take the derivative of my strain energy with respect to a force. That means this thing's going to go away. I'm going to get a length. We'll call it a displacement, delta. If I take the derivative of my strain energy with respect to a length, what do I want to call my length? We'll call it delta just for sanity check. My squiggly deltas here are partial derivatives. They're partial derivatives because strain energy depends on x, y, and z. So you can't take an ordinary derivative in which you have only one thing that it depends on. You have to take partial derivatives. That's not going to matter too much in this class for us. A lot of our goal in this entry-level structural mechanics course is going to be anytime we see a partial derivative, is there a simplification we can do to turn it into an ordinary derivative? And it turns out there are. Why do we do that? Because partial derivatives are a nightmare to do anything with on pen and paper. Like, you're not even guaranteed to find a solution. And if you are lucky enough to find a solution, you're not guaranteed that it is a unique solution. Both of those things you are guaranteed if you have ordinary derivatives. So, brief aside. This symbol means partial derivative of strain energy with respect to delta, which is the length or displacement. So if this gives you a length, what does this give you? I think I heard it here. Force, yeah, exactly. Yeah, we'll call it P. I'm kind of stumbling over my choices for variables here because of the difference between external forces and internal resultants. I'm trying to keep those separate for us. So we'll call this P, but it doesn't, it's not going to matter too much. The important thing is partial derivative of your strain energy with respect to a force gives you a length. Partial derivative of your strain energy with respect to a length gives you a force. This is just in dimensional analysis. Like, really, it's just literally from saying, here's the energy or strain energy, newtons and meters. I could take a derivative of it with respect to length, and I'm going to get a force. I could take a derivative of it with respect to a force, and I'm going to get a length. However, this observation makes it really easy to calculate and approximate the deformation of complex structures. What it allows you to do, and I'm going to change the notation here very slightly in a second, but what it allows you to do is it allows you to, so this top one here, let's focus on this top one. This top one allows you to calculate the deflection at any point in your structure in any direction you want. And all you have to do is take the derivative of your strain energy with respect to the force acting at that point and in that direction. I'll say it again. Well, actually, you know what? I'm not going to say it. I'll draw it. So say I have an object here. Here's my beam. Maybe it's sitting on a little post here. Maybe it's sitting on a roller over here. And for some reason, it's really important for me, if I know what the deflection is right here, I want to know what the vertical deflection, so the deflection in the, I don't want to draw that. It's going to seem like I'm drawing a force. If I want to know what the vertical deflection of that red dot is, all I have to do is write down the strain energy and then take the derivative of that strain energy with respect to whatever force is being applied at that point in that direction. So that means if my if I want to know the deflection, if I want to know the deflection here in the vertical direction at that red point, I just need to take the derivative of my strain energy with respect to the force that's being applied there, and I'll calculate my deflection at that point. What's crazy about this is that it even works if there's no force being applied there. You can just pretend there's a force applied there, and you still get the right answer. We'll talk about how to do this, but I guess I want to make that point because it's really powerful. It's powerful enough to the point where even if there's not a force where you want to know the deflection, you can add a fake force there and still get the right answer. This one does the opposite. If you know the deflection at a certain point, you can take the derivative of your strain energy with respect to that deflection to calculate what the resultant force is at that spot. So if you know a bar is being pulled down a certain amount, and you're really interested in understanding what the reaction force is at that point that it's being pulled, this bottom one will calculate that for you. I think I wrote them out of order, but this one in orange is known as Castigliano's second theorem. And this one in green is his first theorem. I'm going to change them just ever so slightly to really emphasize the point that what you're doing is you're able to calculate the deflection at some point I by taking the derivative of your strain energy with respect to the force at that point and in that direction. And that's really what these subscripts here are trying to note, that you're specifically taking the derivative of your strain energy with respect to the force at that point and in that direction. Same thing goes for the bottom one. These are Castigliano's theorems. They tend to intimidate folks at first appearance for a couple reasons. One, they involve partial derivatives, which in practice is not going to actually matter much at all for us here. Two, they can intimidate folks because our strain energy is often written inside of an integral. And I find that students, when asked to take a derivative of something that sits inside an integral, are not exactly sure how to proceed. The cool thing is, and I probably could have assigned this for you to check, you can either, it doesn't matter, you can either differentiate before integrating and then integrate, or you can carry out your integral of your strain energy and then differentiate. Either way, you're going to get the same answer. So don't let the fact that it's sitting inside an integral mess you up or intimidate you. You can either differentiate, leave it inside the integral, integrate later, or do the integral completely, then differentiate, you'll get the same answer. The third reason is that point that I mentioned about this subtle point of, if you want to know the deflection at a certain point in a certain direction, there needs to be a force applied there in that direction. That's not hard when there is a force applied where you want to know it, but it can be a little tricky when you have to add that fake force, because I think engineers are, this is like, I feel like this is the first time you're ever adding like a fictitious force to your free body diagram. But I don't know, it's not that bad. So we'll go through that. But before we do that and actually try to use these theorems, let's take a break and come back around like 10:08. And if anyone has questions, you can ask them while we're on break. I'm happy to chat. All right. What questions do you have for me? I think this theorem is probably easier to see first put into practice on a really simple problem. And then we can kind of add complexity and show you why it's useful. This really simple problem I'm going to do, you can solve 10 different ways. You don't need to use this theorem for. The power of this theorem is generally in complex loading problems or complex structures. So if you have multiple loads and moments acting on something, or a curved bar that's connected in various ways to walls and other components, all of this still works. But we're going to start super simple. So let's go with an example here. We're going to do this example twice. Once we're going to ignore transverse shear, and the second time we'll do it with transverse shear. So here's a cantilever of length L. We'll call its thickness 2h. It's not going to matter for this first part of the problem. We will call the y direction down, so that it's positive down. And we will apply a shear force at the end of the beam of magnitude P. Okay, if we just deal with bending, we say, all right, you look at this object and you say, what's happening? Well, there's no axial force on it, so it's reasonable to assume that it's not under any axial stretching. There's no torque, so there's no twist. There might be transverse shear depending on the size of this thing. So we'll first calculate it without it, and then we'll come back and see if it matters. So really the only thing this thing is going to do is bend. We know the bending energy of our beam is going to be the 1/2 times the integral of P. Well, I shouldn't say that. Let me do this a different way. 1/2 times the integral of M over EI. That M is squared dx. Now, our force, our shear force applied to the end here, is going to induce a moment that is the force, and the value of that moment is going to depend on where you are, right? So it's going to be your force times where you are in the x direction. So it's going to be M could be thought of as force P times x. And we're going to integrate over M squared. So we can write and say this is going to be 1/2 the force squared x squared over EI dx. At this point, it's up to you. You can either apply Castigliano's theorem here, or you can integrate this over the length dx. I forgot to put integration limits on there. It'll, of course, be from 0 to L. Or you can integrate this thing from 0 to L and then apply Castigliano's theorem. You're going to get the same result, but that's up to you. Well, let's integrate first. So what does the integral of this thing do? This thing equals P squared L cubed over 6 EI. Is that right? cubed 3, yeah, that's right. Everyone's comfortable with that? Pretty straightforward. If I want to know the deflection at the end of the beam, I'm picking the deflection at the end of the beam because that's where I've applied the force. If I want to know the deflection at the end of the beam, then what I need to do is simply say that the deflection, I want to make this a little bit clearer here. So what I'm going to do is I'm going to go back to my drawing, and I'm going to label this point here capital A, and I'll label this point capital B just for clarity. But what we're saying is I want to calculate the deflection at A. To do that, I need to take my strain energy, take the partial derivative of my strain energy, which in this case, well, I'll write this, hold on, I'll say this. I'm going to take that derivative with respect to the force applied at A. The key thing here is that the subscript on the force and the subscript on the deflection are the same, which means physically that the deflection we're solving for is at the point that the force is applied, but also, and this is hard to show in this notation, that the deflection is in the direction that the force is applied. The force is going down, the deflection has to be going down too. Now we said, well, let's approximate our strain energy. As an energy that only has bending. Now this is pretty easy to do. You have a derivative of this thing with respect to p. It's p squared, so you're going to get a 2 on top here. This is going to be 2/6, so 1/3. And so the deflection of your beam is going to be p L cubed over 3 EI. Pretty straightforward, pretty easy to use. Normally, if you want to calculate the deflection of your bent beam, you're going to have to do solve the elastic curve problem, where you're going to integrate 4 times, apply your boundary conditions, or I guess you could solve it with second order OD and apply 2 boundary conditions using your moment. But nonetheless, this is pretty simple, and you calculate the deflection of your beam just by simply evaluating the partial derivative of your strain energy with respect to the load that you've applied there. All right. Let's make it a little bit more complicated. Let's say that maybe we need to worry about transverse shear. If we need to worry about transverse shear, we also need to account for 1/2 the integral over the length of alpha shear force squared over GA dx. Now I'm not going to make you calculate alpha, but I am going to show you what alpha is. So that way you at least have some evidence that you might know how to do it. So let's take alpha out. So alpha, if you remember, equals the area over I squared times the integral of q squared over the width squared dA. Here, let's see here. This is a little bit of a pain. What do we have? We have, I'll tell you that Q for a rectangular cross section. Oh, that was not what I wanted to do. Q for a bar with a rectangular cross section is equal to B over 2 times the height squared minus y squared. We know that Q has to depend on y because we're going to be integrating over the area, and we know that there should be a y stuck in here somewhere. We're going to integrate over area. And this quantity is also something you can really easily calculate by hand. Like area is h times, it's a rectangle. Area is h times b. I is h cubed times b over 12. So you just have to do some algebra. And what you'll find is that if you do that algebra, a over I squared is going to equal 9 over 2bh to the fifth. The weird prefactors come from the fact that you're squaring you're squaring I. And so then this integral becomes 9 over 2 b h to the fifth. Now I said that the height of this bar was 2h, which means you're integrating from negative h to positive h, or it's the same exact thing as integrating from 0 to 2h. It's the same. Oftentimes people do the integral centered around the neutral axis. So this is negative h to h of q. What did I do here? Oh, it's q squared. Yeah, okay, perfect. Nope, we're fine. Okay. 1/4 h squared minus y squared, that quantity squared times b dy. So where does that come from? Well, I squared the, I got b squared here over 4. So I got 1/4. This whole quantity gets squared, that's squared. So then I get a b squared over b squared. Why did I get this extra b? I don't know. I would think that b would cancel out. I think it might be because it gets. I'll have to double check that. I don't know why that is not. Maybe that b doesn't go there, or maybe the b, my definition of alpha is off. Well, oh, no. It's because I integrated over the width. And so I changed this from an area integral to a length integral. So the b squared and the b squared canceled out, but then we integrated over the width, we got another b back. And that's why that b is there. Sorry. Momentary brain freeze. This looks horrendous. But turns out, if you do this integral, the answer is almost 1. It's 6/5. You can do this by hand. I don't know why you ever would in this digital age. I would drop this into Mathematica or Alpha and have it do it for you. Some of your other professors might balk at that. Too bad. So you basically, I told you alpha was a number. Alpha here is 6/5. So now we can go back up here. And I would like all of you to calculate, tell me what the answer is if we say that u is approximately equal to the bending energy plus the transverse shear stress. Then delta at A equals what? My hint to you is that you don't have to redo the bending part. So this should be pretty straightforward. You probably can't see that on your practice. There we go. So take a minute and calculate what the deflection is now that we're including both bending and transverse shear. All right. Hopefully you got something like I got, which is that the additional term is like a 6/5 PL over GA. You probably can't tell exactly by looking at this if you were doing this in practice. What you should probably do is throw some numbers in here for your bar and see how much it changes your answer. I'll give you a hint, not much. Why? This first term, they both have a load. The first term has a load times a long number, the length cubed. The second one has a load times a long number, not cubed. This thing is going to be a small correction to this first one. Sometimes that small correction would be vital. Sometimes it might not matter at all. Depends on your application. But this is how you would handle it. I'm going fast because there's a couple things I want to cover. But Castigliano's theorem is typically pretty straightforward to apply. And it gets better. It not only works for forces and displacements, You can also use it for taking derivatives of your strain energies with respect to a couple, or a torque, or a moment, and that won't give you a, well, look at your dimensions. If you take a derivative of your strain energy times a couple has units force times distance, so you're going to get something that's dimensionless. What's dimensionless? The slope of your curve is dimensionless. So if you take a derivative of your strain energy with respect to your couple at some point, it'll tell you what the slope is at that point. And vice versa, if you take a derivative of your strain energy with respect to your slope, at that point, it'll tell you what the couple is at that point. So that's one way that Castigliano's theorem becomes even more powerful. A second way is, are your strain energies written in terms of the integral over some continuous dimension? Just like any integral, you could also discretize that object. And instead of having an integral over something, it could be a summation over all the, say, forces and geometric properties of each component. So say you had a truss, like 6 bars and 6 pins. You could write down a different version of Castigliano's theorem, which would be a discrete version, which looks like this. Your strain energy could be, for example, a summation, not infinity, and a summation over all the various, sorry, I'm going to change this to J so we're not confusing things. All the various loads, or the loads on each member, has the modulus of each member, cross-sectional area of each member. So this is the same thing, right? It's instead of having it be like force squared over 2 EI, it's integrated over a length dx. This is a summation, force squared times the length of that element over 2 times the modulus of that element and the area of that element. Same thing as the integral, we just discretize it, and that's where the length appears. And using this, the first theorem can be written like this. Summation of J on the I. This is the first theorem, but this approach could be taken for all of them, and it would look very similar. I know from experience that if doing derivatives or handling things with integrals at all is intimidating for students, handling summations really messes people up. But this literally is just saying, like, add them up. Like, you get the summation is just like, if there's 5 things, there should be 5 terms. Add them all up. Each term is going to have its own E, its A, length. Take derivatives. of the internal resultant with respect to the external force that's being applied at the point that you're interested in. You calculate these internal resultants n the same way you would in statics, method of sections, method of joints, whatever is relevant for that problem. But this would be used for something like a truss. All right, we have 10 minutes left, and I want to, yeah, I think we can do this. I want to show, excuse me, I want to show you an example with the fictitious load. Give me 1 second to remind myself. Okay. So for instance, let's look at this problem. The idea with a fictitious load is, here's an example. Let's look at a problem with two bars. They're connected by pins. And one bar is, oops. Is thicker than the other. You can think of this as like a string and a rod or something. Doesn't matter. And this thing is going to experience a force in the vertical direction. We'll call that force P. Everything's the same here, so they both have the same length. There's some angle here. And we'll call the point that we're interested in here, we'll call this point B, call this point C, and this point D. Two bars have equal lengths. The key difference here is that their EA is different. Just by looking at it, you can see the A is different. We'll just pretend that EA is different. So if these bars are the exact same, completely everything is the same, EA is the same, length is the same. If you were to pull down on this thing, the deflection at this point B would be straight down. However, if these bars have different EAs, so let's take this bottom one being stiffer. If you're going to pull this thing down, this bar is going to be really hard to stretch relative to this bar. So what's going to happen is this thing is going to be able to stretch a bit. This bar is not. You're actually going to move a little bit horizontally one way or the other, depending on the ratio of EAs. Does everyone see that? Like this thing will not move just straight down if one can stretch. Pull down, this thing can elongate, so this thing can move vertically and move diagonally that way. Or vice versa. The other way, sorry, we'll move this way. Because this thing is gonna, no, I had it right, yeah. This thing is gonna want to stay at the same length, but this thing is going to be able to stretch, so it's going to move down a little bit, but it's also going to move to the right. So if we want to use Castigliano's theorem to figure out how far point B is going to move to the right, we can't do that. There's a force at point B, but it's in the wrong direction. Our force at B is moving down. We can use Castigliano's theorem immediately to tell us what's going to happen if it moves down. What we can't do is use Castigliano's theorem to tell us, well, is B going to move to the right or the left? We can fix that by adding a fictitious load at B. And that means taking a fake load, which I'll put with some dotted lines here. We'll call that fake load Q. And pretending there's a load at B, which we'll call Q. Now I'm going to do this for the sake of time, but you can use kind of a statics analysis to say, well, I'm going to have some reaction in BC, which is the internal resultant in rod BC, an internal resultant in rod BD, let's see here, well, vertical force P, and a fictitious force Q. And from geometry, we know how to do this, right? We know the angle here is theta, theta. And so we know that we can write a force balance in the two directions as NBD plus NBC is equal to sine theta for the vertical component. And then you just have a sine flip times cos theta for the horizontal component. The way you use this is you include it in your force balance. You take the derivative, right? Our Castigliano's theorem says take the derivative of the internal resultant with respect to your load. In this case, it's going to be with respect to the load Q, because that's the direction we care about. Take the derivative of it with respect to Q, and then after you take the derivative, set Q equal to 0. Okay, I'm going to say that again. You apply your fictitious load. You include it in your force balance. You take the derivative as required by Castigliano's theorem with respect to that fake load. And then you set the magnitude of that load to 0. Okay, so for instance, we can solve these things for NBC. Why do I want to solve for NBC? Well, I want to take the derivative of NBC with respect to Q. So I solve for NBC, I'm going to get 1/2 P sine over sine theta plus Q over cos theta. And same thing, we can solve for NBD equals 1/2 P over sine theta minus Q over cos theta. With these in hand, now I can do what I want, which is I can take the derivative of my internal resultant with respect to Q. So I have this as a function of Q. We added this because we need to take the derivative of the resultant at the point we're interested in the direction we're interested in. So Q is applied at point B in the horizontal direction. That's what we want. So therefore, we can say partial derivative of NBC with respect to Q equals 1 over 2 cos theta. And similarly, NBD over Q 1 over 2 cos theta. Now in this problem, Q goes away after the derivative. If it doesn't, this is the point where you would say the magnitude of Q is 0. I will, after I take my derivative, I can set Q exactly equal to 0. All right. And finally, we can say the deflection at point B is going to be equal to, let's go back to our discretized structure. It's going to be N L over E I times the derivative here. So let's write this out explicitly. I might go like 2 minutes over, just bear with me. I'll try to go as fast as I can. NBC over EBC ABC times partial NBC partial Q plus NBD EBD ABD partial NBD partial Q. And that's all times length because they're both have the same length. And we actually have already done those derivatives, so we can substitute them in and solve for our final answer. I apologize for rushing. And the deflection, our fictitious load doesn't appear. And as a sanity check, we know that if the cross-sectional areas, E and A, were the same, there would be no horizontal displacement. These two terms would go to 0. Our horizontal displacement would go to 0. Sanity check. I rushed here. For the fictitious load, you need a force in the direction and at the point that you want to use Castigliano's theorem. So you just add one, a fake one, use it to calculate your derivatives, which you need at that point in that direction. You need your derivatives at that point in that direction. Then, if Q still appears, just set Q equal to 0. Apply Castigliano's theorem. In this case, we use the discrete version because we had a discrete structure. We had two things, sum from J equals 1, J equals 2. And then we solved for the end result. Okay, I'm sorry for going over. I have one last thing to tell you, and that is I want you to practice this. And so I have a brief homework assignment that we'll have due, let's say next Tuesday. And it's just 4 problems. These are problems in your textbook. They're problems 10.1, 10.3, 10.9, and 10.12. If you note on the syllabus, I had asked you to do some reading to go along with this. I think it'll help. Actually, no, let's make the homework due Wednesday. So that way you can, if you have questions, you can come to office hours on Tuesday. That sound fair? So it won't be due in class. You can just email it to me sometime Wednesday.
The problems, like they're the same for both editions?
I think so. If you have the old edition, maybe just take a picture of them and send them to me, and I can double check. I don't think they changed much, especially in that section. I've checked before, but I can't remember. So just send me an email with the problems if you have those. So let's make this due Wednesday. So that way you can come to office hours if you have any questions. But please do the reading alongside of this. I can't cover everything in as much detail and as much examples as I'd like to be able to in this time. So do the reading. Hopefully it'll help cement some of these ideas. It's not a ton of reading, it's like 3 pages, but it'll have some example problems that will help you. Thanks for letting me go over. Have a nice weekend.